Okay, so I think you may agree with me for for a calculus class, Calc 2 class, there hasn't been a whole lot of calculus being done over the last two sections. And you would be right, this has mostly been review. We now are going to do some calculus. We're going to do some calculus of parametric equations, right? So let's make sure you understand. So I'm going to give you the derivative for a parametric equation. And I will gloss over the, 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 the proof as well as the idea of limits and things of this nature, if you will just make sure that you understand what you're trying to do. Okay, so you give me your attention for just a second, and I will spare you all the details, although that doesn't quite agree with me. So, what are you trying to do? Well, you have some curve, right? You have some graph, and that is in the graph of some parametric equation. With me? There's some x equals y equals equation that when you graph it looks like what we have here. Now, to find the derivative of that parametric equation is to find the slope of, again, some line tangent to the curve at a single point. Right? We want to know the slope of that line. Because if we know the slope of that line, and of course the slope of is constant throughout the entirety of the line. So if the slope is 3 at this point on the line, the slope is 3 at this point on the line, the slope is 3 at this point on the line. So in other words, if we know the slope of the line tangent to the curve at some point on the curve, then we know the slope at that point. And since the only thing that this blue line and this black curve have in common, the only thing is this one particular point that is of interest to us. If you know the slope of the line, then you know the slope at the point on the curve. So how do we do that? Well, again, here's where I now just grant you the derivative. So dy dx, the derivative for a parametric equation. Now remember, parametric equations have the parameter t. But all that you need is to take the derivative of the y portion with respect to t and divide it by the derivative of the x portion, again with respect to t. For parametric descriptions, it should be clear that dx dt cannot be 0. Okay. So this is where our journey begins. We're going to just practice some quick derivatives of parametric equations using this equation. This is actually fairly easy to memorize, but what you do want to make sure you write in your notes is, well, what about second derivatives, third derivatives? So notice what is different. Well, first let's notice what's the same. Notice with the first derivative, it's divided by dx dt. With a second derivative, it's divided by dx dt. With a third derivative, it's divided by dx dt. So it's always being divided by dx dt for higher order derivatives. But the numerator is different. So what we end up with is you have to take, this is what's important. So let's do this. Define the second derivative. You have to know the first derivative, because you're then going to take the derivative of, with respect to t, of dy dx. I hope that part right here makes sense. Then if you know your second derivative, you'd have to take the derivative with respect to t of your second derivative to get your third derivative. I hope that makes sense. I won't, if it doesn't quite, then maybe it will as we proceed. So let's start with something very basic, right? Let's go ahead and do, we want to find dy dx for the curve, and I'll write it in its parametric form. X is equal to sine of t, y is equal to cosine of t. So this you could graph this if you're still in parametric mode, and that would be the parametric equation for that curve. Now, the derivative, of course, would be a function, and in this case, our function of what? Of t. So we plug in a t, and we should be able to get a slope. So how do we proceed? Well, remember, and I'll go ahead, and this is from the previous page, dy dx is equal to dy dt divided by dx dt. Okay, so you know what we got to do. We need our derivatives. So first things first, let's find dy dt. Then after that, we'll find dx dt, and then we'll set up a quotient. So okay, so dy dt. So the derivative, we would be taking the derivative of cosine, which is just negative sine of t. Now dx dt would be the derivative of sine, which is just cosine of t. All right, so now dy dx is going to be equal to dy dt, which was negative sine t, divided by dx dt, which is cosine of t. Now that is your derivative. Of course, if you look this up, you more likely would want to write sine divided by cosine as tangent. So you would more likely want to write that as negative tan of t. So not too bad, right? Let's try another one. So this one will, it's more the same, but they do ask us a little bit more information. Let's make sure we understand what is asked of us. Let me crop out this part. And let me crop out this part so I have a little bit more space so I can make that a little bit larger. Okay, so let's go. So for the curve given by the following parametric description, x is equal to the square root of t, y is equal to 1/4 t squared minus 4. All right, now it says we have a restriction that t has to be greater than or equal to 0. All right. Now, notice that this restriction need not come out of the fact that, like, I can take the square root of 0, but that's why it's saying that you can't be less than 0. But there's the idea, what I'm trying to point out to you is this particular restriction is born from the fact that if you want to stay in the real number system, we can't have negative radicals. What I want you to understand is if we're firing a missile and we're interested in what happens from 2 seconds after launch until impact, then I could write t greater than or equal to 2. Even though that doesn't come from the restrictions of the square root of t, it could just simply happen that I'm only interested in what happens 2 seconds after liftoff, after launch. So this is an implicit restriction because it comes right from the fact that you can't have negative radical square roots. And then when I put t is greater than or equal to 2, that is an implicit restriction because it just happens that we only care about what happens from 2 seconds onward, okay? But nevertheless, so here's your parametric description. I have that written down. And what do we want? We want to actually find the slope, so not just the derivative. We want the actual slope and the concavity at some point. All right, be careful. Don't look off to the graph here because you don't want to just walk away with, because remember, you have to be able to produce this graph and you would have to be able to zoom in enough to, if possible, to even answer some of these questions. So let's stay with me through the analytical portion of it right now. So the first thing, if we want to find a slope, we're going to need a derivative. We need dy dx. So to find dy dx, we know that that is dx dt, I'm sorry, dy dt divided by dx dt. So, all right. So let's go ahead and find dy dt, and then let's find dx dt, and then we'll get our derivative. Okay, so let's start with dy dt. So this is fairly simple. If the best thing to do here is, since y is equal to 1/4 of t squared minus 4, just distribute that 1/4 and then take your derivative, right? So fairly easy to do. You would get dy dt is 1/2 of t. All right, now for dx dt, again, just like you've practiced numerous times, it's better to go ahead and write the square root of t as t to the power of 1/2. And then it's easy to find dx dt from there. And what would you get? Well, you would get 1/2 t to the power of -1/2. All right. So let's go ahead and form our derivative. So dy dt is 1/2 of t, and dx dt is 1/2 t to the -1/2. Okay, now we want to make this a little bit simpler. Okay, -1/2. So let's go ahead and do that right now. So 1/2 divided by 1/2 is 1. So that leaves us with t over t to the -1/2. Well, if you have like bases, when you divide, you subtract your exponents, right? So that's t to the power of 1 minus, because we're dividing, minus what? Minus -1/2. So we end up with t to the power of 3/2. Did I do that right? I think I did. So t to the power of 3/2. All right, so we'll take that dy dx as t to the 3/2. Let's take that to the next page. So dy dx is equal to t to the 3/2. And now I'm getting all the work out of the way up front, because I need to, not only do I need to know the slope, I need to know the concavity. So let's now, if I want to know the concavity, if we were in class, I'd ask you how many derivatives do I need, and you would tell me I need 2 of them, a second derivative. Well, I'm going to go ahead and write. So for the second derivative, it's still divided by dx dt, as I mentioned, except now you have to take the derivative of your first derivative. That's what's important to understand, is the mistakes that I see. Does it make sense? This makes sense now, but when you're doing a test, sometimes this little stuff can escape you. You're taking the derivative of the first derivative, right? This is dy dx inside here. This is not dy dt, right? That's not what goes inside here. It's dy dx. So, all right, let's go ahead and write that out. So that's going to be, I'll go ahead and keep the notation. So we got to take the derivative d of dt of what? Well, what is dy dx? Well, it's t to the 3/2 divided by dx dt, which we already saw that dx dt was 1/2 t to the -1/2. Okay, so let's go ahead and take that derivative. So the derivative of t to the power of 3/2 would be 3/2 t to the power. Now, if I have 3/2 is $1.50. If I take away $1, I would now have 50 cents. So t to the 1/2 divided by 1/2 t to the negative 1/2. All right, well, let's finish this up. So $1.50 divided by 50 cents, right? So it takes 3 50 cents to make $1.50. So that equals 3. And that's going to end up being t, I got it since I'm dividing, that's going to be t to the 1/2 minus what? Minus negative 1/2. Well, 50 cents plus 50 cents is $1. So 3t. That's my second derivative. All right, now let's switch gears and let's go back to the question. So the question was, find slope and concavity at the point 2, 3. Now, let's make sure you understand this is a key part. The point they give you is an xy point. So here's my first derivative, here's my second derivative. Now, do you see that the first derivative and the second derivative are functions of t? So I don't know what to plug in for t, but I can find what to plug in for t from this point. So ready? How are we going to do this? So we're going to go back and so pay attention to me real quick. You can pick either one of these equations. Okay, I'm going to pick the first, x equals the square root of t. So when x is equal to the square root of t, now what I need to do now is use this point in this equation to solve for t. Very simple. I know that x is 2, so I'm plugging in 2 for x, and I need to figure out, let's just say, at what time is x equal to 2? At what t is x equal to 2? Well, so if I do that, 2 is equal to the square root of t. That would mean that, so we got to square both sides. So that would mean that t is equal to 4. All right, now I needed that step to go to this, answer this question. So now that I know that t is 4, let's start with the slope. Right? What is the slope at the point 2, 3? Well, so let's use dy dt is equal to t to the 3/2. And hopefully you're already anticipating. I now know what to plug in for t. So 4 to the power of 3/2. Well, 4 to the power of 3/2 is 8. So that's my slope. It's my rate of change. Now, let's find the concavity. Now, it's the concavity at the same point, 2, 3. Well, my second derivative was just equal to 3t, so hopefully you've guessed it. We now know that t is equal to 4, so I got to plug in 4 here for t. So that means 3 times 4, or 12. So that's my second derivative. But what is the concavity? Well, since 12 is a positive number, we know that it's concave up. All right, let's go back and now look at the graph. So at the point 2, 3, we should have a rate of change of 8 and a positive concavity. So at the point 2, 3, notice that you have a rate of change of 8, that's positive, that's good, and notice we have positive concavity all throughout this, this trajectory. All right, so far, so good, right? It's not, derivatives of parametric equations are not that bad, except when they're that bad, right? So here's the problem that we run into. Now this last problem was really nice because there's only one tangent line at that point. But here's the problem. Here's the problem. So many times we'll have parametric equations that loop back around on themselves, right? You can imagine, and I'm no cosmologist, I'm no astronomist, but you can imagine some type of meteor on a current trajectory, but then you have some type of large, say, star or some other mass that pulls this comet back around, it loops back around, and then sends it off on a separate trajectory, right? So now, life is okay unless you are trying to find the slope at that point where the graph crosses itself twice or more times, right? So in other words, you would think that we would have you can think of it that we would have a negative slope when it's approaching the star. Then after it's been slung around, we would have a positive slope as it proceeds, right? So then how do we proceed with this problem? So let's take a look at our equation. So we have a type of cycloid that we're interested in, and we want to, so it says the Perlet cycloid given by the following parametric description crosses itself at the point 0, 2. So that's what you're seeing, it crosses itself. We want to find the equations, not the equation, the equations of both tangent lines at this point. All right, do you understand the question? So there's some line that models this. I know it's not in y equals, but y equals mx plus b, just to give you an analog for this first tangent line and the second tangent line, x plus b. All right, we need those equations. But what do you need to find equations? Well, you need slopes. You need a point and you need a slope to find equations. So let's go ahead and get the obvious out of the way. So I'm going to need dx dt, and I'm going to need dy dt in order to get a derivative. Okay, let's start with dx dt. So the derivative of what I'm highlighting right now is fairly easy. Dx dt would be 2 minus pi, and then the derivative of sine is cosine. So dx dt is 2 minus pi cosine of t. All right, and now let's take the derivative of y, dy dt. So not bad. The derivative of 2 is 0, and the derivative of cosine is sine. So that's going to be, or negative sine, actually. The derivative of cosine is negative sine. So do you see how, I want to make sure you understand, this is going to be minus pi times negative sine. So it's a minus a negative, right? So that's going to end up being a positive. Positive what? Positive sine. Pi sine of t. Okay. So dy dx is just the quotient. So dy dt divided by dx dt. So that's just going to be pi sine of t divided by 2 minus pi cosine of t. All right, so far, so good, not that bad. Now, why does this get hard? Well, what we need, let me write exactly what we need to proceed with this problem. So we need let me write what. So this is what we need. What value is t at the point 0, 2, right? Because 0, 2 is an xy value. I need to know how much time it took to get to that point. All right, so what is the t-value? Well, to do this, because it crosses twice, what you're going to do is, and I'm going to go ahead and write x equals 2t minus pi sine of t, and write y equals 2 minus pi cosine of t. So those were the original equations before any derivatives were taken, right? Okay, so at the point 0, 2, so I'm going to have to take 0, plug it in for x, and I'm going to have to take 2 and plug it in for y. And the idea is that you would get, let's just go ahead and, it doesn't really matter how you do this, but if you take, let's take this one. So if you have 2, y is equal to 2 equals 2 minus pi cosine of t, we now need to solve for t. So let's first, you and I agree that if you subtract 2 from both sides, we get 0 is equal to negative pi cosine of t. Now I'm going to go ahead and take this negative pi cosine of t. I'm going to take this to the next page. Okay, so we left off with 0 is equal to negative pi cosine of t. And let me make sure you see that negative symbol a little bit better. Okay. So then now you have to ask yourself then, well, what the heck is t? All right, well, the question you're asking is, so t is an angle in this case, right? So what angle makes cosine equal to 0? Well, if t is equal to pi over 2, well, cosine of pi over 2 is 0, and 0 times negative pi is still 0, so that works. But what else works? Well, it is true that it would be 3 pi over 2, but we want to think of it as negative pi over 2. And the reasoning behind that is because you have to go back to, I'll write it here. I don't really think I need to elaborate too much, but so you can divide both sides, listen, I'll just do it. So you can divide both sides by negative pi without losing any solutions. So 0 is equal to cosine of t. Cosine inverse of 0 is equal to t. And what you have to remember is there were domain restrictions on the inverse of sines and cosines, right? So what we end up with is a t-value equal to, and you could do this, you would do the same here with your x value, but what you end up with is the following. You would get all of that work so that you can say that t is equal to plus or minus pi over 2. Right, so we're getting 2 t-values. And now let's go back to the picture just so you can understand. So here's this comet coming, right? Now, let's just say pi, I know that this is a fictional example, right? But at pi over 2 seconds, it's here at this point. Then it starts to loop around, and then, or I should say, so at negative pi over 2 seconds, right? That's what I should have said. And again, I told you this analogy is going to fall apart. But again, so using the common analogy, so negative pi over 2 seconds, whatever the heck a negative second is, we have the comet at this location, and then pi over 2 seconds later, we have the comet back here at this location. Okay, so we now at least know the t values. But that's not, that what we just answered was when t is equal to plus or minus 2, the graph is at the point 0, 2. That's what this information tells us. At these two times, right, at these two parameters, the graph is at this point. Now, we were asked to do what? We were asked to find the equations of the tangent lines. So the first thing we need, let's think about it, to find the equation y equals mx plus b, you need a point and you need a slope. We don't have a slope. So let's go back to our dy dx. So dy dx was equal to, what did we have? We had pi sine of t over 2 minus pi cosine of t, correct? So how do we find the slopes? Well, you're going to have to plug in pi over 2 in here for t. That'll give you a slope. And then you're going to have to plug negative pi over 2 in here for t to give you the second slope. So I'll just go ahead and write you some notes because I'm going to give you the answer. Plug in pi over 2, negative pi over 2, and then plug in pi over 2. All right, well, here's what we get. We actually get slopes. This is very nice. Dy dx is actually just simply equal to plus or minus pi over 2. Right, so very nice. And that makes perfect sense if you just stop and think about it. Sine of pi over 2 is 1, right? And that would give us pi over, well, cosine of pi over 2 is 0. So that would be pi times 1 divided by 2. So that's pi over 2. Now, if you plug in negative pi over 2, this would be negative 1 times pi. Again, cosine of negative pi over 2 still zeroes out, but that would be divided by 2. All right. So now, let's actually form the equations. So, we're going to use this slope, these slopes, I should say, and we're going to use this point to get to our equation. So y sub 2 minus y sub 1 is equal to m times x sub 2 minus x sub 1. Right, let's plug in the information we know. So we're plugging in for m, we're plugging in for 0, and we're plugging in for 2. All right, so we end up with y minus 2 is equal to negative pi over 2 x. And we get y minus 2 is equal to positive pi over 2 x. These are the two equations. You can look back to your picture just so that you can see that that's the tangent line. So the equation of that tangent line is as follows. Okay, no, I'm sorry, I'm pointing to the wrong thing. That's the equation of the parametric description. These are the equations of those tangent lines. All right, so I hope you understand that that's because you understand that we had to do all this extra work because we are forced, or at least conditioned, to stay in rectangular coordinate systems. It's so much simpler if you just, this is not for this class, but if you just simply stay in parametric equations. This t equals pi over 2 is the tangent line. And t equals negative pi over 2 is the tangent line. So much easier if you stay in parametric equations. But since we wanted to go to, we wanted our lines in rectangular, then we had to go backwards. All right. So this last one, what I've done is I've taken a picture of the majority of the work, because what we're doing is I'm just introducing an arc length formula. Okay, but this is an arc length formula if you want to stay in parametric form, right? Clearly, arc length is I don't have to debate you on how to be able to know the arc length would be important, right? Would be useful. So we want an arc length formula for parametric equations, so that you don't have to go from parametric back to rectangular, so that you can use the old arc length formula to find the arc length, right? You want a new arc length formula so that you can find the arc length the way it sits. And this is it. So, okay, so there is, I won't go through the theorem too much in detail. So, by the way, smooth, well, there is, I mean, like I could describe a smooth curve as, one that is continuous, where there's no sharp corners or edges. But that is obviously, that's very sloppy, and you're right. That's not mathematical to say it has to be smooth, no sharp edges, no sharp corners. That's not there. So there is a mathematical formal definition of what smoothness means. Not for this class. So just take my my description of no sharp corners. But so you have some curve that's given by some parametric description. When they say the curve doesn't intersect itself on the same interval a to b. So in other words, like, it's okay if the curve does something like this, but you don't want it to intersect. This won't work. You can't use this formula if you want the whole arc length that I'm drawing right now. You would have to end up getting multiple arc lengths and adding them. So, but as long as your curve, right, as long as your curve doesn't intersect itself over some interval, then this is the formula that we're going to use. So I'm gonna there is going to be some parts here where I'm going to just show you a picture of all my work, and you're welcome to just work it out and look at what I've done. So first off, let's see if we can understand the question. So it says we're going to use that formula. So the last question of this section. So we have a circle of radius 1 that is rolling around the circumference of some larger circle. Let's look at a picture really quickly. So here's our circle, right, of radius 1. And notice that circle is just rolling around some other circle of I don't know what they say, of radius 4. Yeah, so it's just rolling around this circle. And then what we're going to do is we're going to take a look at how you could trace, like if you had a if you had a particular point on that little circle that's of interest to you as it rolls, right? You can see how your point, like if you had a nail in a tire, right? You can see how, and actually I'm going the wrong way. You can see how it would just trace out the following curve. Now I could erase the circles, and although it's not very well drawn with this stylus, what we have, this, right? Again, not very well drawn. This is the shape of the parametric curve that we're actually trying to find the arc length of. So hopefully that picture helped you. So let me continue. So as shown in the picture, so the epicycloid that is traced by a point on the circumference of the smaller circle is given by, there it is, the parametric equations. Now, what we want to do is we want to find the distance traveled by the point in one complete trip around the large circle. So very cool. All right, I need to go ahead and get some things out of the way, all right? So dx dt, let me write that. So just take the derivative, that's negative 5 sine of t plus 5 sine of 5t, and then dy dt. Well, that's going to be derivative of sine is cosine, so that's 5 cosine of t. And now the derivative of sine is negative cosine, so that's going to be minus 5 cosine of 5t. Okay. So we don't need to form the derivative because what we need is, notice that we're going to take the square root of dx dt squared plus dy dt squared. So what I'm going to do now is go ahead and first let me tell you that, listen, it is much easier. So let me erase what I just wrote here. This is the way we're going to do this. I would suggest doing this too. The symmetry is such that if I knew the arc, so listen, see what I have it outlined in red if you're looking here? If I knew this arc length, I could just times it by 4, right? And that would be the total arc length. Agreed? So let's not go from, we're only going to go from here to here, and then we're going to multiply it by 4. All right, ready? So let me write the arc length formula. So S is equal to 4 times, now where did that 4 come from? Well, I just said if you have to rewind, you'll see where the 4 comes from. Now I'll go ahead and give you the bounds in just a second. So the square root of, and you can see why I'm not going to do this by hand and while I have you in video, because this is a lot of little, nothing super hard, just a lot of tedious work here. So negative 5 sine of t plus 5 sine of 5t. That's going to be squared plus, so we got, that's dx dt squared. Now let's take dy dt squared. 5 cosine of t minus 5 cosine of 5t. And all of that has to also be squared. And then there is a dt over here. All right. So what I'm going to do is, let me show you first. So you would have to find how much time it took, or the t value, from 0 to here, which is not bad if you think about it for just a second. Like, don't you agree with me that this is basically just 90 degrees? Right? Pi over 2? Not 90, don't use degrees in calculus, right? Use radians. So this is just, to go from here to here is just a pi over 2. So it's going to be, that's why we're not going to go from 0 to 2 pi, because that would be the whole circle. We're going to go from 0 to pi over 2, and then we're going to times that by 4. Now, this is the part where I skip pages and show you a lot of little work, okay? Here we go. Feel free to pause it if you'd like, but if you want to integrate, you're going to have to get this thing a little bit nicer, a little bit, so you're going to have to foil everything out, combine like terms. Now, you would have to do the same thing for, that's just, that this is me foiling out one of these. And this is me, or I don't think yeah, this is me foiling out the other one. Okay, so this right here and this right here is just the FOIL process. All right. Now what I'm doing is I'm gonna, so looking at, I'll highlight them one more time. I can factor out a 25 out of both of these, but we end up with the following. Now, we got a lot of things to reduce, but anytime you have a sine squared plus a cosine squared, that's a 1. And then you're going to end up with another even sine squared 5t plus cosine squared 5t, that's still also 1. So that gets us to here. Now, since I factored out a 25, that's the square root of 25 times 5, so I'm sorry, not times 5, but which reduces just to 5. So this is where we're going to pick back up. So that leads me to S equals, well, it's 4 times, remember it was the square root of 25, so that's 5, so 4 times 5, so that's 20. We want to integrate from 0 to pi over 2. And what we had left at that point was 1 plus 1, so that's 2. And now I want to show you one more thing. So this 2 sine of t sine of 5t minus 2 cosine of t cosine of 5t. This is why you should have paid attention in your trigonometry classes, because this is a pain in the butt to integrate unless you're willing to accept decimals. But if you want an exact answer, and I assume your employer is going to want an exact answer whenever possible, you would have to use a difference formula, right? So you're just, notice that that's just a difference formula where cosine of alpha times sine of beta, we want it to look like this. Hold on. We want it to look like this. Right now it looks like this. My apologies, I can't really read this handwriting. Yeah, so we basically have the following form. We want to rewrite it. Okay, so if you will allow me, and you can work it on your own, that should get you to 2 minus 2 cosine of 4t. All right, again, that's still pretty nasty to integrate, but you could go a little bit farther with that, because cosine of, this is a double angle formula, cosine of 2t is equal to 1 minus 2 sine squared of t, but we have cosine of 4t, so you'd have to, you end up with a product there. So all in all, we end up with S is equal to 20, which we times the integral from 0 to pi over 2. And man, we did a whole lot of work to get to here. 4 sine squared of 2t, which we actually can finally integrate. Okay, so so all of that work to get to something that we can integrate. Or you can give your employer a decimal and just say, well, it's about this. And then the employer says, well, what the heck did I need you for? I could have just put that in my calculator. All right, so when we end up with, I'm going to go ahead and write it, so we're almost done. We're almost done with this section. 0 to pi over 2, square root of 4 sine squared of 2t dt. All right, well, look. You can break this up into the square root of 4 times the square root of sine squared of 2t, right? That's perfectly fine. So that means you get 2 times, well, what is the square root of a square? Well, let's write it. So this ends up being 20, 0 to pi over 2, 2 times, well, if you take the, you get the square root of a square, so that's just sine of 2t dt. All right, well, let's bring that 2 out front, so that's 40, 0 to pi over 2, and sine of 2t dt is what's left. All right, so that's very easy. You can walk through the rest of this, and then the integral, so that you would end up with what do we got there? Negative 20, so you just use u substitution at this point. Negative 20 cosine of 2t, which you have to go from 0 to pi over 2. All right, so f of b minus f of a gets us to 40. There it is. There's the exact arc length. No decimals, none of that silly stuff. All right, I will see you in the next video.